Hi, everyone. Welcome to the active remote sensing event. This is our host, Dr. Ruben Delgado, who has a PhD in physical chemistry from the University of Puerto Rico. He is an assistant research professor at UMBC for the last 15 years, and he leads the atmospheric LiDAR group. Thank you.
Thank you, Dr. Cardona. So my name is Ruben Delgado, as I was introduced, and I'll be talking to you about some of the research activity that we carry out at UMBC, and the effort supports research in the fields of air quality, wind energy, and meteorology. So just to kind of give you a little bit of background of what is this Joint Center for Systems Technology that I'm part of at UMBC. So it's a research center between the university and the NASA Goddard Space Flight Center in Greenbelt, Maryland. It was established in 1995, and us that are part of JCIT, we are affiliated through different academic departments of the university. So we are contributing to the overall teaching and research at the campus. One thing that we do, it's heavily meant to be engaged with students, and we mentor graduate and undergraduate students that want to work with faculty in different research teams that are aligned with NASA and other federal agencies.
I hear him. What was it?
Are we good?
Yeah, please keep yourselves muted if you're not asking questions. Thank you.
Yeah, okay. So just to kind of give you a little bit of background as in the part of the introduction. So I was a chemistry major as an undergrad because I had an opportunity to do research with lasers. That kind of presented an opportunity, career opportunity later on to do LiDAR, which is kind of what I've been focusing for the last 15 years, doing remote sensing, and I use that for applications in atmospheric chemistry and physics. The group itself that I'm leading at UMBC, we focus, like I said, in air quality, wind energy, and meteorology, and as well as the development of this technology to study those areas. The work that I'm going to be showing today, and that what we have carried out historically, is all due to students like you attending here in the audience today. We have a very diverse set of majors, and with that said, my research is one of the most diverse as well, culturally and ethnicity on the campus. So we have majors from atmospheric physics, biology, engineering, geography and environmental systems, math, statistics, and physics. And the research itself, the last few years, we've been trying to explore more into the, kind of opening areas in the social sciences, kind of focusing on public health, planning and policy, environmental economics, and sustainability science to kind of, come full circle. And one way to kind of relate that social science to our work is, the work that we carry out is all due to taxpayer money, right? So we need to be able to link the work that we do to a societal benefit. So the areas that we tend to focus on are kind of using this laser type technology to look at how much there is of aerosols, gases, and winds in the atmosphere, and to know, for example, how their concentrations or the quantities of these different substances, how they change with height. That allows us to kind of have a good understanding of what are the chemical and physical properties that are of these species in the atmosphere. The LiDAR activities, and we'll get into what LiDAR means in a slide or two, These activities support state and federal agencies. And here in Maryland, we have carried out activities for the Maryland Department of the Environment, as well as the Energy Administration. And at the federal level, we are heavily involved with NASA and NOAA for satellite calibration and validation measurements of their forecasts. In a recent effort, we've been working with the EPA on a new ceilometer network that we're implementing for them. So by using this LiDAR data and combining with other data sets, it allows us to kind of provide scientists and policymakers of all the relevant information to have a better understanding of what's happening in the environment. So this image here in this slide, it kind of puts into context our research. So for purposes of the work that we do, we combine instruments like the ones shown here in the middle panels, which either these are lasers that would shoot shoot light to the atmosphere. That light that goes out to the skies can bounce off of cloud particles, dust, or smoke, and we can collect a return signal. From that return signal, then if we combine that with measurements that are carried out at the surface and with satellite images, then we would have a 3D picture of really what's happening in the atmosphere. And I'll be showing some samples of the combination of all these data sets and how it helps kind of do a forensic kind of CSI of what's happening in the environment. So the principle that we use for our measurement is known as LiDAR. LiDAR stands for light detection and ranging. So what it consists is having a laser being shined to the sky, and that would bounce off of aerosol particles or dust particles, cloud particles, smoke particles in the atmosphere, and that photon will come bounce back, and we have a telescope that has a wide field of view that allows us then to collect those photons, and those photons of the laser light is then received in a detector, and from that detector it gets sent to a computer, and then we can kind of analyze our signals. The nice thing is because we know how much time that laser pulse takes to hit something in the atmosphere and come back, that allows us then to determine at what height in the atmosphere it was. So the technique itself allows us to have a better understanding of what's the makeup of the atmosphere. So it tells us, how much particle there is per height. If there is a cloud going by, we know at what height is that cloud occurring, and that's very important for aviation. Also, what might be some of that composition of the cloud. There's ways of knowing how much either ice particles or water vapor or liquid phase water is within those clouds. The other thing that we can know is it's what we label boundary layer growth and dynamics. And in a very simplistic way, that's what that refers to is that the air that we breathe is confined to the lower part of the atmosphere, close to the surface. So if you want to think about that lower level atmosphere, think about it as a box. So what we are capable of doing with this technology is to know the depth of that box. So if it's a very shallow box, it means that pollution is going to be close to the surface, so most likely can affect us because we can breathe it. But if the box is the bigger, the wider the box, means that there's more room for that pollution to kind of dissipate into the atmosphere. So Well, going back to how we carry out this research, right? So we combine the the data from different platforms. So the images shown here are for the top panels here are satellite images. That this here shows smoke kind of moving across the mid-Atlantic. The star here is actually where Baltimore is at. So you can see smoke kind of moving across the region. Those images in the top, there's a satellite indicator that is for aerosol optical depth. You know how much light gets attenuated from those plumes, and that's what we see here in red. So you can kind of correlate that plume of smoke coming through the region with these satellite measurements. The nice thing is that now going back to the type of measurements that we carry out, we can then know at what heights there are particles in the atmosphere. So this particular event here, this is the smoke that you're seeing here in these images. And we can see it kind of coming crashing to the ground. Here, the red mean the darker scale color means that there is more amount of that of a substance. So you can see that there's a layer kind of descending at the surface. The intensity is kind of increasing as time goes by, but then when that layer of smoke kind of breaks in and mixes to the surface, then you see an increase in the concentrations. And we'll go more into this case later on. The difference between these two images is just that by changing the color scale, you're able to see some of the structure, what's happening within this lower atmospheric layer. If I would have kept the same scales, this image to the right would have been saturated. It would have been all kind of like dark red, black. So, once again, one of the key messages that we want to bring in today is that we have this technology that, and we use it to pursue societal benefits, and we have a wide range of stakeholders that are benefiting from, agriculture, water quality, energy, and disaster response. So this boundary layer monitoring that I spoke about. So the nice thing of this technology is that it allows you to monitor a different type of weather events. So you can kind of look, for example, when there's clouds in the atmosphere, and these is what's represented here for this very narrow band in red color. When we know when it rains, and we know how the signal looks when it rains as well. There could be many layers of these particles in the atmosphere, so we know also where they are. Can they impact the air that we breathe near the surface? And so it provides it's a very kind of it's novel technology that we are kind of making folks aware that should be exploited for societal benefits. So there's a lot that can be done in terms of meteorological applications. This here is just showing an example. This is from a few years back. We were in a field campaign in Kansas, and you can see from the satellite image, kind of these wave-like structures in the atmosphere, and these are all clouds. So the clouds kind of moving over this site called here FP2, which we had located our instruments. And so you're able to capture that from these images. So that's all that kind of oscillation that you see there. Those are those clouds kind of rolling in. And one thing that we've been able to kind of show and make aware federal agencies is that the data itself should be collected. There are similar instruments in the National Weather Service that just report what height the clouds were, but doesn't show the rest of the structure. So it's one of those things that there's a lot of opportunities of interdisciplinary research because there's a need for the data and you have to kind of come up with very clever solutions to collect it. In terms of air quality, this is just a quick picture of work that we carried out 2 summers ago, and it's actually kind of still ongoing in terms of the data analysis and so forth, in which we deploy a lot of these profiling sensors at Hart Miller Island in the Chesapeake Bay. The interest on doing that is more to kind of identify what's the difference in ozone concentrations in the on land and water. Why ozone? Ozone because for purposes of air quality in Maryland, ozone is the pollutant that we tend to violate the minimum air quality standards. A lot of it has to do with it's natural, it's naturally made, but there's some of the precursors are associated with NO2 emissions, but are going to be associated with traffic, and some of them to organic compounds that come from different power plants in the region. So having a good understanding of how things kind of move across a region and how the chemistry can evolve, that can be accomplished with this type of technology. So for this particular campaign, one of the things that we were looking at, what might be those sources of pollution, right? So depending on the time, on the time of the day, the winds across the bay may vary. And so we were able to correlate that to the different power plant, fuel reservoirs, and even the poultry and agriculture industry in the Eastern Shore. So for purposes of air quality, it's one of the things that come in handy, this technology, is to try to determine if it's a local source or something that came from elsewhere. One thing that we see is that obviously these aerosols can remain in the environment for long periods of times. The ones that kind of remain the longest in the atmosphere circulating are the ones from, for example, that came as a result of a volcanic eruption. So if they can make it to the what is known as the troposphere, so 12 to 15 kilometers in from the surface, they can circulate for several months in the atmosphere. So one nice thing also from having this technology is that a lot of these air quality monitors, they're all at the surface. So they are going to miss what may be happening above you, right? So this technology comes and helps in because it kind of allows to identify, where things at. Also, it comes in handy, as I said, in terms of, are we as a pollution, a local source, or something that came from elsewhere? The example that I'm going to be showing now, it's from an event that happened in 2015, and some of the images are going to resemble ones that I showed earlier. And the reason why I'm showing the smoke events is because during the summer, you see a lot of wildfire activity happening in the west coast, Pacific Northwest, and Alaskan Canada. So just happens that the wind and the weather patterns are kind of allow for the transport of that smoke to come to our area. In terms of this particular event, it happened. It all started because of a lightning strike in Saskatchewan, Canada. And so that smoke was visible from space. Here in Baltimore, we're using this LiDAR technology. We're able then to monitor what's happening in our neck of the woods, and that's how we knew that there was a layer of something above us, and we were able then to identify that layer. So the two bottom panels are from measurements done at the surface from a monitor in UMBC. The other one is in Beltsville, Maryland, at the Howard University Beltsville Research Site. And what we can see here, that as this layer is coming down and kind of increasing the amount of pollution in the surface, which is kind of shown here with the darker reds, that's at this time period that where you see the increase happening in this time series. For the this is and it's not just something localized to UMBC and Beltsville lower area. Something that kind of happened across the state, because you can see that kind of increasing as well with all the different aerosol monitors throughout the state. Using some of the products that are available to the community, it does allow us then to try to pinpoint what might have been the source of the smoke. So this image here is a Google Earth overlay of the hazardous mapping system fire and smoke product that NOAA has, the National Oceanic and Atmospheric Administration. So they're, one of their line offices is the National Weather Service. So from the different combined satellite measurements, they can detect the different locations where the satellites are seeing smoke. So, and that's what's represented here in that green, red, and yellow kind of shades, where you see the smoke plume kind of in the western half of Canada. The lines in red, blue, and purple are from what is known as high split, which is a air mass back trajectory analysis that NOAA also provides. And what that allows you to do is to then determine, for example, if something that you saw in your neck of the woods, like in this case, if I go back, we said, okay, what are we seeing at around 3 kilometers, right? What's this layer here? So we are then able to run it for several, for 96 hours, saying, okay, tell me where that air mass was 96 hours ago, prior to coming over Maryland. So with that said, each of these colors represent a different height. And so it's showing that, that the air mass that was really coming through, it came from those locations where the smoke, or the forest fires were occurring. So the nice thing of doing this, there are ways of kind of knowing the chemistry of what's coming in, to Baltimore, but the analysis of that takes several days, and for the most part takes actually months. So with this technology that we are able to kind of tell on real time, at least in a qualitative sense, what might be the type of pollution that it's over Maryland. So going back to the satellite images, so this smoke here, once again, you see it kind of moving across the region. The one thing that satellites are great because it gives you a global perspective of, or top-down perspective also of what's out there. But one thing that they cannot do is to say at what particular height that's that smoke is at. So with the instruments that we have, we are able then to say, okay, what was observed was at a given height. It just happens that there's once again, there's chemistry that can be used to verify, chemical composition analysis to verify the makeup of these particles, but there's at least a 3 month to 6 months delay of those samples, because the samples are collected in filters. The filters then are shipped to a secondary location, that then a thorough chemical analysis happens. So from one of the EPA air quality networks, we were able to obtain that data and then look, for example, in the in the mid-Atlantic and kind of northeastern states, what was the makeup of those particles that reached the surface. It just happens that the potassium ion and organic carbon, they are markers for forest fires. So we can see that there was an increase on their concentrations for that period of time, where that kind of matches up for that window that we were seeing the smoke coming across Baltimore. What I'm showing now is from, once again, it's a different type of event, but because we have this technology, we can classify what's in the air. This is from a winter pollution event that happened in the year 2009. All these different images here are from weather balloon launches that were carried out and at the Dulles Airport, and so they show, what was the temperature in the first 5 kilometers of the atmosphere. So the key thing is when you see a little kink like this, the kink there means that you can relate the temperature in the atmosphere as it changes in height to that size of that box where the air that we breathe is contained. So what it shows is that especially from the 7th to the 9th, you see a box that is very close to that the width is very shallow. So the pollution is going to be really concentrated near the surface. So this is the time series from the LiDAR observations for those days. So you can see periods of times where the intensity increases near the surface. And it just happens that with the instrument that we have, we can identify if the particles are either spherical or non-spherical. And that helps classifying the particle type and or the nature of those particles. So what it shows is that for that particular series of days, we saw a lot of non-spherical particles. So, what's the source? What's the source for them? So to kind of corroborate what we were seeing, we do have this other sensor that gives us a snapshot of what's happening as the atmosphere as a whole. And the key thing to look into this figure is that showing these curves that have, show probably particles that the diameter of the particles are by 5 microns. So, and that the particles itself scatter a lot of light. They don't absorb that light. So that tells us, it might not be in a typical pollution, urban pollution type aerosol. It has a kind of characteristic of something that looks like dust, that doesn't have that is a non-spherical particle. But then the question is, is it, what kind of dust or soil type could it be? So we were able then to do so this time series here on the top kind of shows the increase of the aerosols at the surface. That just happens, that coincides with those periods that I discussed before. Then you had the non-spherical particles. So a colleague of ours was able to take samples on the rooftop of our building. And so what you see in the bottom right image is a scanning electron microscope image. And so you can see many of the particles collected. And so, just to give you a kind of perspective, so this is about 10 microns and, about I think it's 2 centimeters down here, close to an inch. So that's so that tells you, there's a lot of those big particles. So when you look at the chemical makeup, we realized that the composition, that what you were seeing here, was due to rock salt. And that goes back to even, what had happened prior to this event. It was one of those cases in which we had a heavy snowfall prior to February 7th. So I think it was on the 5th, several inches of snow on the ground. A lot of the roads in the area were treated with road salt. And, because a lot of road salt was deposited, it just happens that after we went through the snowfall, um, the temperatures rose to up to 60 something degrees in February, which is very unusual. So now you have the excess amount of road salt on the road. So as the cars are driving by, they're pulverizing it, and all that is kind of being lifted up into the atmosphere. So, and because the box was kind of shallow, because of, kind of like what I showed in the time series that showed the temperature with height, that didn't allow for that pollution created by the road salt to kind of really dissipate. So, so far, I've been showing you, why this technology is great to have. But one thing that we've been able to communicate to others is the need to establish networks of these systems. So we've been involved, and different folks from the group since 2009, and some different National Academy of Science reports on monitoring for weather and air quality. So we've been able to put out that message. And one alternative that we have promoted is the use of ceilometers, which is, it's really no different as the LiDARs that I've been talking about, only that the price on the technology and the instruments has gone dramatically down. So it's a cheap alternative to a LiDAR, and a reliable one. So what we've been able to do is to compare all these different type of instrumentation that is commercially available, and to say, okay, how good or bad it is in terms of the quality of the signal, and the different software that comes with the instruments in order to obtain different meteorological variables. So we have some of these systems of our own, and we have a few others that are a little more advanced, and we can then do intercomparisons to have a good sense of what's the best technology that there is out there if you were to establish some new network. So that opportunity kind of led into what we are kind of headed right now, which is what we labeled the Unified Ceilometer Networks, which is a joint effort between NASA, NOAA, and the academic community. And so we started with a test project of 6 systems along the 95 corridor between Delaware and Washington, D.C. And now we have expanded to close to, we are currently 30 plus sites, and it will be 40 plus definitely after the end of the summer, and across the United States, to measure and monitor this particle pollution that I've been talking about. If you're interested in taking a look at some of these images, you can either go to our website, and you can see a real-time data display for these images, and a lot of the things that we're doing is, that we're kind of developing, is being developed by students in computer science and physics and chemical and mechanical engineering, is trying to come up with a very dynamic way of presenting the data. So when you go to data to the portal, you can kind of look at what's happening throughout the different sites that are throughout the United States in real time, or you can go to the archives and look into more of the historical data. A lot of the work that we have carried out is to kind of determine the height of the box, and that's what's being represented here in the black dot. So we have come up with mathematical expressions and that are kind of capable of then of identifying different layers in the atmosphere. Last not least, I'm just going to show you an example from about a year ago, in kind of as we were rolling out the network from a controlled burn at the Marine base in Quantico, Virginia. So on March 8th, I guess year to date, they announced that they were going to be burning about 2,000 acres at the base. It was going to be managed by the Forestry Service of the Marine Corps. They didn't give any warning to any of the local and state authorities, and we knew about them because the smoke made it all the way to Baltimore, and we were able to track it down through Facebook posts from the base. So what happens, and this is the part that, if they would have had a meteorologist on staff, or they would have consulted with folks, people would have said, oh, today is not a good day to burn, because that box, that where all the air is and the pollution can be concentrated, was a very shallow one. And it was shallow throughout the whole region. So what happens is that, all of a sudden, throughout different locations in the 95 corridor, there's this, heavy smoke presence, up to the point that you can smell it. And you can see as it kind of moves along, the 495-95 corridor, how, there's an increase on their concentrations as it goes from south all the way to locations west and north. Just happens that in there's a couple of monitors in the state that can measure black carbon. So we see also a spike in an increase in concentration that as well in the later afternoon. And that is actually coinciding now with what we are seeing as from the observations of this network. So, this is just 4 images from locations kind of, south to north and east. And you can see, for example, that the intensity of the signal is increasing around 19, UTC, which is minus 5. That's about 2 o'clock, 4 o'clock local time, 4 to 6 o'clock local time. And you can see as it kind of moves north, the increase is happening at a later time. So we are able to track that and know that smoke was really confined close to heights close to the surface. This image here is from when it's a satellite image and shows, this is the fire from the Marine base, and you can see how that plume kind of is increasing and it kind of moves up north. There's a secondary fire that happened in the area as well that kind of blended, in locations north. But that's the source of that smoke, and we were able to capture that from satellite measurements from space. With that said, since the establishment of the network, we've been able, now we have, like I said, 30 plus sites across the U.S., and it does allow to tracking all these events, from as they move across the nation. So the heavy, the heavy wildfire activity in California in the month of September of last year, we were able to track all that plume kind of coming across the nation. And this here is just a satellite image kind of showing the darker white. Those are clouds images. Those are clouds in the satellite image, but everything else that kind of looks kind of hazy, milky, that's smoke. So in summary, some of the take-home messages is that, with this technology, be able to kind of identify if the pollution within the Baltimore area, if it's due to natural or man-made aerosols, and if it's, you know, a local source or due to transport from a distant location. The data itself, it can complement some of the air quality action day evidence efforts that the state carries out, especially the Maryland Department of Environment, and the data has been used in the past for that. Because we have now this network that we're developing in the US, you know, we can monitor really what's coming across our neck of the woods, and kind of inform the forecasters at the state agencies, and then they would make alerts to the general public. So, you know, one thing that you know, part of the take-home message of this presentation, that if you combine, you know, several of these sensors, you know, it gives you a nice way to kind of have a good sense of what's the temporal and spatial type of evolution and changes that you see in all these type of pollutants. So the last part of the talk, I want to kind of just make you aware of research opportunities, especially for the students here today, that you can carry out with the research group at UMBC, and especially if, you know, some of them are going to be, you know, and while I'm making the announcement to the general public, you know, if you have an interest in pursuing research, you know, it could be outside of this, you know, different topics that I presented today. So, but we do have opportunities, especially for students. And it's, if you're transferring to UMBC and you want to, you know, take advantage of an opportunity that can provide you financial support, and depending on the fellowship can provide even tuition support, please reach out. So the areas, like I said, is very interdisciplinary in that sense. One thing that the students like about these opportunities is that you get involved, you know, in field campaigns and doing all the measurement, all the stuff all the measurements that I was showing here today, they're all made by students, right? You know, folks like you in the audience. So a lot of opportunities to work out with students and faculty and scientists from the different agencies. One particular fellowship, a research undergraduate research fellowship that I'm promoting here today, that also has a summer internship program, is one that is sponsored by the NOAA Office of Education, and particularly one of the 4 centers that they sponsor, which UMBC is part of, which is known as NOAA CSERT, the Center for Earth System Sciences and Remote Sensing Technologies. And that center itself, you know, UMBC is a partner with University of Puerto Rico Mayagüez, University of Texas El Paso, San Diego State, Hampton University, and University of Puerto Rico Mayagüez, as well as City College of New York, which is the lead institution. So the kind of the area, our research thematic areas, some focused on coastal resiliency, other ones in atmospheric hazards, water prediction and ecosystems, and social sciences. So, you know, you can have a very diverse set of students from different majors kind of working on these research areas. So the way, if you were transferring to UMBC and apply to this fellowship as an undergrad, the minimum support that we provide is $12,000 a year for 2 years, and that can be used to cover your tuition, stipend, and travel. We do provide opportunities for the students to present their research work at national conferences, and also this opens opportunities to do internships as well at national labs. That's one opportunity. If you eventually want to pursue a graduate opportunity and get a master's or a PhD, we can technically, we can actually provide you support, and you know, at no additional cost to you. We can provide you, you know, funding for stipend, tuition, and travel as well. One program that may be of interest to several of you is the summer bridge program. So if you're actually planning to transfer to UMBC and become a student in the next fall, please, shoot me an email, and I'll be sharing my email at the end of the talk. It's a 8-week paid summer internship opportunity. It pays about $4,000 for 8 weeks. You have to be a U.S. citizen, and you need to have a GPA of 3.0 and above. And so, there are going to be workshops that kind of discuss, the relevancy of the work to social science, remote sensing, and you get to learn some coding as well. As part of that program, we also kind of give you proper training for you to apply to other NOAA undergraduate scholarship programs. So we have had a good success rate of students that kind of join the summer bridge program and then get later on apply and are awarded the NOAA scholarship. Last and not least, starting the summer of 2022, we are going to be, UMBC is funded with Coppin State, Morgan, Hampton, Howard, and University of Maryland Eastern Shore to be funded in a NASA Science Activation Grant, and it's known as the Student Airborne Science Activation for Minority Serving Institutions. So if you're transferring to any of these universities and you would kind of want to pursue a summer research opportunity, I strongly encourage you to apply. Applications will open in the fall of 2021 for the first cohort of students that will be part of an 8-week program in which students will spend time at UMBC, Hampton University, and the NASA Wallops research facility in Southern Maryland, Virginia, kind of learning about very diverse set of topics. But one of the key things is that you get to kind of do experiments and interact with NASA scientists in airborne missions throughout that summer. So that's kind of a unique opportunity for students. With that said, I would like to acknowledge then all the folks that kind of sponsored a lot of the activity that I presented to you today. And last and not least, it involves, as you can see, a lot of state, local, and federal agencies. With that said, I'll be glad to take any questions.
No questions were asked on the chat. So if you would like to ask Dr. Delgado any questions, this is the time.
I have a question. To apply to these opportunities, do students already need to be accepted into one of the institutions that you mentioned?
For the airborne one, yes. For the one that involves NOAA, if let's say next year you still be at CCBC, you can apply.
Okay, cool. Thank you.
We see CCBC as a partner institution, so there's opportunity for community college students to be involved with an institution like UMBC. So as long as you by the time that you participate in say like in the summer research experience, you're still a student at CCBC. You're eligible. If you're for that matter, if you're transferring to one of those institutions, for the NOAA one, it has to be UMBC. For the NASA one, if you were to transfer, then you would have to apply through the main application portal, but then you would indicate that's one of your that your home institution is one of the partner institutions.
Actually, I had a question. So earlier you mentioned two instruments that were used, the sun photometer
Yep.
and the scanning electron microscope. I was wondering what other ones were used, like to scan for air quality and pollution.
Yes. So those are two. Another one that we use is either a ceilometer or the LiDAR that would generate the more of the colorful images that I was showing earlier. Let me just pull one of those images.
A ceilometer and a what?
A ceilometer or LiDAR. That's one of them.
Oh, okay.
Then there's a series of air quality monitors. So there's monitors for ozone, for organic carbon that they can be used as well to kind of help kind of do that CSI type of analysis of what might be the pollution in our neck of the woods. So it could be a combination. I mean, I'll show you the earlier slide. So it could be a combination of either, if you have them all, that would be great. But even if you didn't have all these instruments in the bottom, if you were to have at least, if you were to have one in each tier, you can tell, there's ways of telling the story like I showed you today. And even if you had either two or even just one, there's ways to kind of correlate or get or derive or kind of do a little bit more quantitative analysis to identify what might be the nature of that pollution.
Okay. I also see an instrument called a radio sound.
Yeah. So the radio.
Top right.
Yeah. So the radio sound would be just your typical weather balloon.
Okay.
And so it would have a sensor that would measure, pressure, temperature, relative humidity, among some of the variables. And then you can have you can have at the end of the balloon a larger type of package if you wanted to do, let's say ozone or any other chemical type of species. But that we use as well. And so we have launched many radiosondes from UMBC and the Baltimore metro area as well.
Can I ask another question about the programs? You mentioned learning how to code. How does that play into this type of research?
Yeah, so one of the way it comes into play, the most basic approach is to be able to generate images like the ones in the bottom row to plotting, right? Some of the data has many, has at least what I would call 2 dimensions. So you can have 1,000 rows and 1,000 columns, right? So some of the coding that we kind of we kind of teach you, the ropes. We're not gonna kind of leave you on your own. So because in order for the work to be fun for the student, we have to make sure that we provide them all the tools. So we will provide you the basic knowledge for you to be able to, let's say, like open one of these data files and to be able to plot it. And then after you're able to open those data files, anything that involves doing the math, there is particular ways that you have to write, the mathematical expression for the software to do the right thing. But those we will cover. So things that we tend to use for some of the images that we generate, we use MATLAB. So if you know some MATLAB is good. If you know some Python as well, that will be beneficial. Or depending on the type of application, if you know some like our ArcGIS as well, those come in handy for some of the work that we do. And if you didn't know any of those three, we definitely kind of teach you how to get familiar and acquainted with them.
Do you ever try to make models to predict what will happen based on the data that you get?
I personally don't, but I do have a lot of colleagues that that's their bread and butter. So I provide the observations for them to kind of make sure that the forecasts of the models are representing properly what there's, what the end product is going to be. So there's a lot of assumptions in those models. So the key thing is to have a data set that kind of resembles close to reality, to the observations, and then from there they can tweak the models to make sure that they properly account for what we have observed.
Ruben, you have another computer science student here, Alan, with the question. He has his little emoji hand raised.
Yeah, go ahead.
How's it going? I wanted to ask, I'm assuming that most of these positions, or sorry, internships are going to be on site. If that's the case, in terms of logistics, how are you guys doing, or what are you guys doing to take precautions for like COVID-19
Yeah, so
related stuff?
since a year ago, so I would say next Friday will be the last. It will be a year since the last day that I stepped, in my office. So since then, we've done everything virtually. So we and I currently, we do carry out our, that's one of the things. Research didn't stop. Our lives did stop, but research didn't, right? And so in that sense, it'd be pretty much been doing everything with virtual tools. So for example, I meet with my students at least twice a week. There's 1 hour that we all meet together, but then I meet individually with the students to discuss, their own work and progress and many other aspects as well. So we are very accommodating in that sense.
Gotcha, thank you.
So I had one more question.
Go ahead.
So I see that this is being recorded. Do you know where I can access it if I wanted to view it later?
Yes, you can email me. My address I just put on the chat is
Okay.
ccardona@ccbcmd.edu. I'm a faculty member at CCBC. And I will be posting this on my YouTube channel, so I can forward you the link.
Oh, okay. Thank you.
No problem. Are there any more questions? Well, thank you everyone for attending, and thank you, Dr. Delgado, for your presentation. As he presented me, I forgot to introduce myself, but he introduced me. I'm Dr. Cardona, and I teach environmental science and physical sciences at CCBC Essex. So my address is on the chat, and so is Dr. Delgado's if you want to contact him directly about any of these opportunities. But I will be posting this on YouTube, so you can request the link if you would like to refer back to it. Thank you.
Thank you, guys.
Thanks for coming.